Hi, I'm Adrian Sampson, and this is a talk about the intersection between approximate computing and probabilistic programming. First, I want to tell you a story. A while back, I wrote an article for the glossy magazine from IEEE called Spectrum, and it terrifyingly got posted to Reddit. So of course, I went there immediately to upvote it, but also to look at the comments, which I knew would be bad, but they had a little bit of a theme among them. The theme was that we were not convincing enough that it's possible to program approximate computers and to get reliable software result. And this is a little bit of an image problem for approximate computing, but it's also something that I agree with. I think that the programmability of approximate computing is the biggest problem that faces it today, and that's what this talk is about. This talk is about two ways that we can hope to make approximate computing more programmable, to make it more possible to write reliable software using approximate programming. And it's a suggestion that those two problems, both of which I think are critical, share an underlying challenge that we can address. The two problems I'm going to call assisted approximate programming and cheap check generation. And they both have a common thread in statistical inference, that if we can solve this one underlying problem, we can solve two important problems in approximate programmability too. First, though, I want to talk a little bit about what it means to express quality for programs, because if we want to provide tools for approximate programmability, we're going to need some sort of input from the programmer that tells us whether we're doing a good job or not. This is an expression that's come up a lot in discussions of approximate programming, and especially in programmability. And it is a general form by which programmers can express what it means for a program to be more or less accurate. What it asks for from the programmer are a distance metric that acts on the outputs of the programs and results in a score between, say, 0 and 1, indicating the similarity between the original program, the output of the original program, and the output of a relaxed version of that program, an approximate version of that program on the same input. And then the programmer also needs to provide parameters that tell us how close those values need to be and what the probability needs to be that those values are that close. What's really important are not the details here, but the fact that there's a fairly general expression of quality that we can use as a goal in writing tools for approximate programmability. And I'm going to highlight it in this green blocky rectangle because it's going to come up many times throughout the rest of this talk. Now I want to talk about the first notional tool that I think is important in approximate programmability, and that's what I'm calling assisted approximate programming. In traditional approximate programming, including some of the systems I've proposed in the past, including Energy, the approach to approximating a program is manual. You want to go from an original program, an original function f, to a relaxed version f prime. And in Energy and other systems, you do this by manually marking the operations and the data in your program as approximate, by telling the system what to approximate, what to leave precise, and how approximate you can make each operation. Assisted approximate programming, as the name suggests, is just providing a limited amount of automation to this process. And crucially, we ask the programmer to provide the tool not only the original program f, but this quality constraint, this blocky green thing that I talked about just a second ago, that lets the tool know how it's appropriate to approximate that function. And I want to emphasize that this is not a new idea. There's been lots of research from lots of really great groups on exactly this problem, but I think it's important that we identify it as a challenge that we're trying to make progress on. The second notional tool I want to discuss is something that's been less well studied in recent years, and that's what I'm calling cheap check generation. Cheap check generation addresses the gap between the fantasy and the reality of how quality might work for approximate programs. You might imagine that in your approximate program, the probability of correctness might be more or less constant irrespective of the inputs, meaning that over all of your inputs, there's more or less a constant probability that you're going to succeed for each of those inputs. But in reality, this is not really the case. And we've seen this in a lot of approximate programs, where there's a certain range of inputs where there are corner cases that do a lot worse than the rest of the inputs. And if you just look at the average probability of success across all of these inputs, you lose these. In fact, you end up being more conservative because you have to account for the low probability areas of the input as well as the high probability areas. We can address this if there were a system that were able to factor out the parts of the input range that don't do well with the approximation we're proposing. And that's what a cheap check would do. A runtime check could possibly identify those inputs on which the approximation is unlikely to succeed, and instead substitute in the fully precise version of the computation. By doing so, we get not only a higher average probability, but we can be more aggressive in our approximation. So in terms of that blocky green rectangle, the idea behind cheap checks is to take as input an original function f, the original program, the relaxed version f prime, and a measure of the quality of those programs, and then to produce the inputs x that make that quality high, that is, that satisfy that quality constraint. Then we can develop a runtime check that checks whether an input belongs to the set that is high quality, or whether it's not in that set, whether it's likely to be a low quality input, and fall back to the precise version of the execution. So these are two important tools that I think approximate computing research should be focused on. Now I want to convince you that after a little bit of desugaring, these fall back to these have underlying them the same core statistical inference problem. And if we can solve this problem, we can solve both of these component tools and provide new ways of writing approximate programs reliably. First, there's a desugaring step, where here I'm depicting an approximate program where some of the operations are approximate. It's also possible to rewrite this as a garden variety probabilistic program where all of the randomness in the program is explicit. This is important for applying probabilistic programming techniques to these approximate programs. You can see here I've entered in an error term, a random draw from a probability distribution that models the approximate hardware that the approximate program is running on. Then I think it's pretty easy to see how we can phrase the assisted approximate programming problem in terms of this desugared representation of an approximate program. Assisted approximate programming boils down to filling in the distribution parameters for these probability distributions in the program so that the quality constraint is met. So the assisted approximate programming involves putting these wildcards, putting these holes in the distribution parameters for these probabilities, and finding those values so that the quality constraint given by the programmer is upheld. Once you have these distribution parameters, that tells you how approximate each of the operations is allowed to be, and we've solved the assisted approximate programming problem. For cheap check generation, instead of putting those question marks, putting those holes in the parameters of the error distributions introduced during the execution of the program, we'll instead introduce those in the inputs to the program. So we'll have probability distributions with inferred parameters that reflect those inputs that uphold the quality constraint given by the programmer. Now we'll be inferring the probability distributions from which inputs have to be drawn in order for the quality to be high. Then a cheap check just involves checking the probability that an input was drawn from those inferred distributions. So now that we have phrased both of these important problems as one core underlying problem, as finding the distribution parameters for probability distributions in probabilistic programs, how are we going to go about actually solving this underlying problem? There are many challenges. The first step, though, I think, is translating from the original program into the representation of a probability distribution, into something like a Bayesian network. And this is something that we've already gotten a handle on in our work in PLDI this year, where we're able to translate using a symbolic execution technique from imperative code into a Bayesian network representation. But this is far from the end of the problem. We need to do now statistical inference based on constraints. In machine learning and traditional statistical inference, the inference is done using a series of examples. So you can tune the parameters of distributions based on lots of input you see from the wild. In our case, though, we don't have a bunch of examples. Instead, what we have is a constraint on the output of the program, and this makes the problem different. Secondly, we don't just have a constraint, we also have optimization objectives. We want to, for example, minimize the amount of energy spent. We want to minimize the precision of the program in order to uphold the constraint given by the programmer in assisted approximate programming. For cheap check generation, we want to maximize the amount of inputs that are considered good and minimize the amount of inputs that will cause fallback to precise execution. In both cases, there's this objective function that we need to minimize, something that is also not traditionally present in statistical inference in other fields. Finally, and perhaps most importantly, the inference algorithms we use have to be scalable. We can't resort to inference techniques that work for small hand-tuned examples. We need this to scale to programs, to entire programs that may be thousands, millions lines of code. So I've told you about the relationship between assisted approximate programming and cheap check generation, two important problems in my opinion in approximate programmability, and how they can both possibly be solved using the hammer of statistical inference with some advances. The overall message I want to leave you with is that we talk a lot in approximate computing about using techniques and listening to research that's been done in numerical analysis, or more relevantly here, in statistics. But the advantages that we can get from statistics aren't going to apply themselves to approximate computing on their own. And statisticians aren't going to build the bridges necessary for approximate computing to take advantage of all that research. It's up to us, the approximate computing people, to find out what the opportunities are and to build those bridges to other fields so that we can take advantage of the knowledge that's been locked away in those fields. Thanks.